Okay, now we should have a pretty good picture of these graphs of z equals y squared and z equals x squared. And that should be z equals x squared, not y equals x squared, the way I wrote it previously. And it's down here, z equals negative 2x squared. And I should have written that in blue. Well, no. Okay, well, that's, there it is. Okay. Now, to do 2y squared plus 1, we start with z equals y squared. We double every y coordinate, and we get z equals 2y squared. And then we add 1 unit, and we get z equals 2y squared plus 1. And that's what we get. Now, where do we get this? Okay, let's go back and do these things. Okay, so your function one variable here, and that variable is x. This function is we just plug y equals 3 in here and simplify, and this is what we get. And we should instantly see this as a parabola because it's quadratic, and we should instantly understand how to graph this thing by transformations and find the intercepts. Okay? That's what you do when you have something, a simple function like this. Okay? And usually you're going to see a simple function. If it's the arctangent of x squared over the third power, or the 3/2 power of x squared plus y squared, you're not going to be able to graph that. Okay? But for simple functions, as I hope you learned in pre-calculus, you got to be able to graph by transformations. Anyhow, so there it is. Okay? What's the derivative of x equals 1? Well, we're going to say it like this: f of x3 then equals negative 2x squared plus 9. So the derivative with respect to x of f of x3 is what? Negative 6x. And that's straightforward. Everybody do that derivative in their head quickly. How do we represent that on the graph? Well, this graph is getting a little bit cluttered, but at x equals 1, this is negative 6. Well, x equals 1, let's see, on this graph, here's 9, right? And here's where x equals 3, so x equals 1 is going to be like here. So up here is the point 1, 6. I'm sorry, 1, 8, right? X equals 1, 7. Okay, if x equals 1, this is 7. So here we have the point 1, 7, and the slope, the derivative, is the slope of the tangent line. And it has slope negative 6. Tangent line at this point has a slope of negative 6. And actually that reconciles fairly well, considering that I had kind of a pointed parabola here. with where this tangent line ought to intersect the x-axis. And you should be able to figure out where that tangent line intersects the x-axis. It's 7 units high here, has a slope of -6, and actually that isn't even close. And if the slope is -6, then it's going to take just a little over 1 unit for it to drop 7 units. So the intersection ought to be closer to here. And there might be something wrong with the graph, but I'll let you think about that. So here's your -6. That's why your slope is -6. And it's not -6 because I can't take derivatives. I can take derivatives, I just can't keep my numbers straight. Apparently it's -4. Yeah, you guys saw it. So I say, yeah, I got to keep something hard on the table so you can throw it and hit me on the head with it and knock a little sense into me. But that's -4. Okay? You got something hard like Nerf balls or something like that. Okay, makes sense? Well, there's the picture. Okay, that's this function. That's this function confined to the plane y equals 3. Now, in 3 dimensions, if this is your x-axis, y-axis, and z-axis, you're in the plane where y equals 3. That would be out here. So you go into this plane, and now you've got this upside-down parabola. Okay? That's part of the picture of your 3-dimensional function. And we know if we go to the point 1, 3, and it's 1, 3, 7, because the z-coordinate is 7, that point up here on the parabola, there's a slope of -4. Okay? And the slope of -4 reconciles better with this, but I still didn't have it quite steep enough. Okay. Well, there it is. So that's this much, okay? And yeah, also graphing the function and showing the derivative. That's over there. Here we have it. Well, we want to do the same thing for the plane x equals 1. Now, just to show there's method behind my madness, the plane x equals 1 on our picture here would be out from the origin, about here maybe. Okay? And that plane would intersect this graph in the y equals 3 plane at a point. Okay? The point being, again, 1, 3, 7. Same point that we get in the 3-dimensional graph corresponding to this. So these two graphs would intersect at this point. The x graph is like this. Well, okay, again, if x equals 1, if 1y equals -y, I had to make it clear that -x squared means -x squared y means you square x, multiply by y, and then make that negative. It doesn't mean you're squaring -x. That would be this, with parentheses around the -x. It's the negative of x squared y. And that's a common misconception that usually experience beats out of you by the time you've taken a calculus course. But if it hasn't, then get it beat out of you now. Okay. Actually, I think that got emphasized by my high school teacher in a Algebra 2 class. But I'm, not sure everybody picked up on it. And I had to think about it. Okay, anyhow, z equals this. Okay, if x is 1, you're going to get a negative y plus 1, because 1 squared is 1, plus y squared. And that's y squared minus y plus 1. This gives you a parabolic graph. And I believe the vertex is at 1/2, 3/4. Not going to go over the pre-calculus of how to find the vertex. Okay? I might write it down here in a minute. I just refer you to a quick video from my pre-calculus class, because that's exactly what they're doing today. The whole section on quadratic functions. And you really have to understand that if you really want to understand a lot of things that you need to understand. And it's easy, compared to what you're doing here. It's easy, but it's kind of a piece of necessary understanding to understand motor variable calculus or even calculus. So you can correct my calculations if you want, but there it is. Okay. I don't have an abundance of room here. And of course, my point is, don't feel bad if you have something about pre-calculus you don't know. Just fix it. Okay? Now, I used z equal 2y squared plus 1. I graphed this, but you know what? I just saw that in somebody's paper and wrote it down without thinking. And that's okay, because I wanted to clarify what that graph looks like, right? And if you got 2y squared, it's because you tried squaring negative x instead of doing the negative of the square of x. Okay, so that's not the right function. So I didn't look at the details of how you calculated that, didn't calculate it myself, should have. But there it is. Okay, so changes your graph a little bit. But graph that one. You take your y equals x squared graph, and you shift it over to its axis of symmetry, which is y. And it's not y equals x squared, it's z equals y squared. Okay, axis of symmetry. Is it y equals 1/2? The vertex on the axis of symmetry, so z coordinate of the vertex is z equals That's how I got the vertex. But you got the axis of symmetry, just plug the coordinate in. So this vertex is at, what's the color here? Okay, 1/2, 3/4. The coefficient of y is still y squared. So to get the graph of this function from the graph of z equals y squared, you simply move it over and up, and you get this. So every point of this graph moves over this far and up this far, okay? So every point moves like this. So, for example, this point would move over this far and up this far. This point would move over this far and up this far, giving you 1, 2, 3 points that you can easily then use to sketch a graph. And you really need to be able to do that, very quickly when the need arises. You don't go to a graphing calculator to graph these things. If it's a complicated function, yeah, you go to a graphing calculator if you can't figure out how to construct it quickly. And then you look at it and say, oh yeah, here's what happens. Okay, well there it is. Now, when y equals 3, you get z equals 9 minus 3 plus 1, which is 7, right? Which, coincidentally, is the z coordinate you get here. So what was the method behind my madness in making up this series of problems? You get the point. Three, 7. Okay, well, again, y equals y squared minus y plus 1. Z equals, if y is 3, z is 7. dz dy is, well, dz dy is 2y minus y, minus 1, okay? Which is, I think I'm getting 7, no, 5. Why do I write 2y minus 1? Because that's dz dy, right? So you can represent that. Slope dz dy evaluated at 3 gives you 5. Well, now what does this say. We note that this point corresponds that 7 looks awfully weird. Maybe a little bit. These graphs are the slices of the graph of f of x, y equals negative x squared y plus, make sure I got it right. Yeah, well, plus x squared plus y squared. In the planes parallel to the xz and the yz planes through the point 137, which does lie on that graph. In other words, if you plug x equals 1 and y equals 3 into this equation, you get negative 3 here, you get 1, and you get 9. Okay, 1 and 9 is 10, minus 3 is 7, right? You just emphasize where that 7 comes from. It does f of 1, 3 is 7. Now you can attempt to sketch that graph. X is 1 and y is 3. And let's say here is 1, 3, and you come up here 7 units. Here's the point 1, 3, 7 in a plane parallel to the xz plane. You have, sorry, to the yz plane, to the xz plane, sorry. The plane parallel to the xz plane through this point, y is 3. If y is 3, then you've got this function here, 2x squared plus 9, negative 2x squared plus 9. So the graph in this plane does this. And that's in the plane parallel to the xz plane. Now, in the plane parallel to the yz plane, you have the graph of this parabola. Okay. And yeah, that's going to work. This parabola that I'll draw in a different color. Okay, so here's the plane parallel to the yz plane. Here's your function. It has its vertex not on the, not through this point, not at the top of it. And you know, when I drew this, I drew it a little carelessly. This point up here is a little to the right. So we have this downward slope looking at your slope. We found here, okay, slope -4. Picture's gonna get a little messy, but we're gonna do it anyway. In the YZ plane, your vertex would be down here, over half a unit and up 3/4 of a unit from the origin, which has been translated to this point, so it's over here and up here a little bit. So you got a vertex here, kind of a z-axis here, and now you have this thing with its upward slope, comes up through this common point, point 137. Somehow I'm missing that point. Okay, the graph is getting locked up. But these two parabolas meet at the point 137. So at the point 137, this parabola has an upward slope. This one has a downward slope. So what are the implications for truncated parallelepiped near this point? Well, first of all, the slope in this direction's got to be kind of a big negative, right? So the top of the parallelepiped here will kind of look like this, whereas the slope in the y direction would be a big positive. So, yeah, let's extend this back here a little bit. So over here you've got something like this. And your picture is going to look something like this. Now that picture is mucked up, so I'm not going to submit it for any prizes. Would have been easier to draw if I'd have given myself more room, so it's a mistake to try to do it that small. But now the point is here, at the point (137), in the x direction, your slope is -4. So it's like you've got this vector I minus 4j, like we did last time. In the y direction, you've got this vector, which is, slope was 5, okay. So you've got, not drawn quite to scale, but you've got these vectors, okay? So this vector is in like your xz plane, the plane parallel to the xz plane. And this vector is in this plane here, just like we've got this with this vector above this side and this vector above this side. Well, this vector is j plus 5k, so this is 1 unit and this is 1 unit. They don't look like it. That's just because of our perspective, because of the fact I didn't draw it very carefully. Okay, what's the normal vector? And what's it normal to? Well, it's normal to the tangent plane. The surface has a shape, and there's a tangent plane at this point that's perpendicular to both of these vectors. Okay. And of course, that's what? That's I plus fx of fx evaluated at the point 1,3 cross k plus fy evaluated at the point 1,3. Which is just what we did last time. So the first thing you need to do is you need to be able to calculate tangent planes. Now we got hung up on the whole process of constructing simple graphs, okay? No offense, they're simple graphs. You should be able to construct them at this point. But since you did have problems constructing them, we had to digress and talk about that. And that kind of hung things up a little bit. Value of f of x, y at 1, 3 is 7. What is the approximate value at 1.013? Well, slope of 1,3 is -4, isn't it?